Okay, so welcome to the Module 2 live classroom session. This is one of the more lengthy live classrooms, so I'll try to go as fast as I can and not keep you here super late. Don't feel bad if you have to duck out and watch the rest of it later. I totally understand. It's just a really large module, probably the largest we have. So the learning outcomes for this module are to kind of understand basic atomic theory, which sounds really complicated, but it's not too bad. Okay, cool. Thanks, Mary, for letting me know. It seems like the transcription's working okay, so I think my microphone is okay. It's like writing down the things that I'm saying, so I think the microphone's good to go. So basic atomic theory, not very complicated, but really what that is going to get into is like the periodic table of elements. That's the thing I really want you to take away from this class, how to use it and whatnot. And then we're going to introduce Avogadro's number, which doesn't sound like anything to you now, maybe, but it will hopefully by the end of this lecture. And to introduce the Bohr and quantum mechanical models of the electron. So there are two labs due. The density of a cube, pretty easy. You're just calculating the density of a cube, its volume and its mass. And then a photosynthesis lab, which is also fairly simple to walk through. These are two like the easier labs, which is good. The module 2 quizzes were 30 points, so that's basically the same amount as the labs. So put some good effort into it. And then again, the module 2 live session response is worth 5 points, and I'll give that to you in the middle of the lecture. So let's just start off with atomic theory and periodic table of elements. I'm going to fly through a lot of these so that I can get to the quiz examples. So if I go really fast, just make sure you go back and review later since this is being recorded. So we use the term atom. Well, what is an atom? Some of you may not really know what that word means. When we talk about an atom, we're talking about the most fundamental building block of matter as far as chemistry is concerned. So it's the building block of all the molecules and compounds that form the matter that we interact with as chemists, right? Medical professionals, right? But what is an atom, right? Well, it's composed of even smaller stuff, so it's not the most fundamental building block, but for chemists it is. We don't really think about what's inside the atom very much, but it's important to know what's inside the atom just so that you can get an idea of kind of their properties. So we'll start off with just the very basic, like what is an atom? Well, an atom is a fundamental building block of all matter, and it's comprised of three different particles. Inside the nucleus of the atom, which is like the center part of it, there's a tightly packed arrangement of what we call protons and neutrons. And these are pretty big particles, but they're all kind of compact really close together, and they're surrounded by this cloud of electrons, which are actually really tiny little particles that kind of orbit around the nucleus. So here in this diagram, you see the nucleus at the center surrounded by kind of a cloud of electrons. Something interesting about these protons, neutrons, and electrons is what we call their charge. It's a really important concept to take away. Protons are positively charged. You just have to memorize that. Electrons are negatively charged. You just have to memorize that. A proton has a charge of +1, and an electron has a charge of -1. So if you have one proton and one electron, you have a neutral atom, right? Neutrons have no charge. They just don't. So you have to memorize those three things. The other thing that you can take away from this is if you look at the mass of the proton and the neutron, you can tell that they're much, much larger than the mass of the electron. So the electron is teeny, 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 tiny, whereas the proton and the neutron are very large in comparison. But despite the electron being very small compared to the proton, it has the same charge, just the opposite charge, right? So they're both 1, even though it's a lot smaller. So how do atoms differ? We have all these different elements, but how are they different? Well, atoms are identified by the number of protons they have. That is the most important. So this is underlined in red because it's probably one of the most important things you can take away from this lecture. Atoms are identified by the number of protons. They can have different numbers of neutrons and different numbers of electrons. The number of protons identifies them. So for example, in these balloons right here, they're filled with helium. And how do you know it's helium? Because if you looked at those atoms, they have 2 protons. Helium always has 2 protons. It might not always have 2 neutrons or 2 electrons. Those can differ, but it will always have 2 protons. Here we have an aluminum can. Why is it aluminum? Well, the atoms in that aluminum can have 13 protons. Aluminum always has 13 protons. It will never have something different than 13 protons. If it doesn't have 13 protons, it's not aluminum. It might not have 13 neutrons or 13 electrons, but it will always have 13 protons. You must remember this is very important. So the fact that all the atoms differ by their number of protons kind of led to this really interesting discovery by a guy named Dmitry Mendeleev. He was a Russian professor that noticed that elements kind of had this repeating set of properties. He noticed that, when he looked at helium, for example, number 2 here in green on this like line of atoms, he noticed that, helium has certain properties, and the one next to it, lithium, has certain properties, and the one next to it has certain properties, beryllium. He noticed that boron, carbon, nitrogen, and oxygen all have the same kind of properties, and that fluorine has certain kinds of properties. But then all the properties between these guys are all different. Helium has different properties than lithium, is different from beryllium, boron, carbon, all these. But what he noticed is that every time you repeat 8 atoms, you find similar properties. So you notice that helium has very similar properties to neon. If you go 8 more numbers in the periodic table, you come up with argon, which has very similar properties. Same with lithium and sodium and potassium and beryllium and magnesium and calcium. So he noticed this repeating set of properties every 8 atoms. So he decided to kind of arrange these in columns and group the similar properties by their columns, and that kind of gave rise to what we call the periodic table of elements, because it's periodic in nature. These properties kind of repeat as you go along the periodic table. So this is kind of what the early periodic table looked like right here. Actually, it's a lot bigger, right? We ended up filling out much more of it as we discovered more atoms, but it's still periodic in nature, and that's kind of what I want to elucidate to you in the beginning of this lecture. First, let's talk about how the periodic table of elements is used. So each of these atoms, right? So here I've highlighted beryllium and I've blown it up a little bit. Periodic table, a good periodic table is going to have 4 pieces to it, right? In each of the element boxes, right? It's going to have the atomic number. If you ever see the letter Z in chemistry, that means the atomic number. The atomic number, very important. Let me like hand wave so that you like pay attention to this. The atomic number is equal to the number of protons. So beryllium, you see, its atomic number is 4. It means that it has 4 protons. It might not have 4 neutrons or 4 electrons, but it definitely has 4 protons. It definitely has 4 positively charged protons in its nucleus. It'll also have the chemical symbol Be. That's the chemical symbol for beryllium. It'll have the atomic mass, which we'll talk about later. It'll have the name beryllium, which is spelled out right here. So those are the pieces of information that you can get from the periodic table that are really useful. There's more that we'll go over later, but this is kind of the basics. Something that you should know about the names, they don't always have the right abbreviation that you're thinking of in your mind. So for example, potassium you might think is PA or PO or PI or something like that, or just P, but it's not. Potassium is K. Why? Well, it comes from Latin kalium. Sodium you might think is SO or like SI or something, right? Well, it's not. No, it's just Na. It has nothing to do with the name sodium. It comes from natrium. So just understand that there's some tricky ones right here. Fe is iron, for example, right? Understand that you might be getting the wrong element if you're not aware that there's some exceptions to these naming conventions. But for the most part, they kind of make sense. Like carbon is C and oxygen is O and nitrogen is N. So let's talk about how the periodic table is laid out. Because it's periodic in nature, because these properties repeat, there's certain things that you can tease out of the periodic table. The first is whether an atom that you're looking at is a metal or a non-metal or a metalloid. Everything on the left-hand side of the periodic table kind of acts in a similar way. They're all metals, and what that kind of means is that they all kind of conduct electricity, and they all tend to have what we call labile electrons. The electrons come and go really easily. So everything on the left-hand side of the periodic table, with the exception of hydrogen, is a metal. Everything on the right-hand side of the periodic table is what we call a non-metal. So the periodic table is kind of divided into these 2 parts, metals and nonmetals. And along the center of this, on the stair-step line right here, beginning at boron, we have what we call the metalloids, atoms that kind of act as metals and nonmetals. Something else that you can kind of get from the periodic table are what we call the main group elements and the transition elements. So we've got the metals and the metalloids, cool. Or the metalloids, the metals, the metalloids, and the nonmetals, right? That's cool. But what we also have is a breakup of the periodic table into 2 different sections. The main group elements, which are these yellow ones here, 1A, 2A, 3A through 8A, and the transition elements, 3B through 2B, down here, highlighted in blue. And they all act sort of different in the way that their electrons are grouped together, which we're going to go over a little bit later. In healthcare, your main focus is always going to be on kind of these top main group elements: hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, phosphorus, sulfur. A little bit down here in the blue, we get some elements that are kind of important every now and then, like zinc, copper, right? These are important. Iron is very important, right? Manganese. But for the most part, you're going to be dealing with, groups 1A and 2A, very important. 3A, 4A, 5A, 6A, and 7A. Periodic table is broken down even further into what we call main group names. So transition metals, these guys in brown, they're always transition metals, but certain columns though have certain kinds of names, and they're actually pretty important. We call them main group names or main group categories. I think it's categories I haven't read here because I think the quiz actually calls it that. But understand that the 1A period column of the periodic table are grouped as alkali metals. That's just the name of anything that's in this column. Everything in the 2A column is an alkaline earth metal. Everything in the 7A column is a halogen, and everything in the 8A column is a noble gas. And I guess the reason that they got names to begin with was because their properties are so very similar in that column that we just started to kind of refer to them as one big group. Lithium, sodium, potassium really act like one another. They have the same kind of reactivity and properties. Beryllium, magnesium, and calcium and strontium, very similar to one another. All the halogens really, I mean, like super similar to one another. The noble gases, same thing. So we gave them names, and it's important for you because, I was a pharmacy technician for a long time in the hospital setting, and you would hear people talk about, oh yeah, like the alkaline earth metals, like we talk about calcium and magnesium, right? Two very important cations in medicine, or the alkali metals, right? You're talking about everything in the 1A column. When you say alkali earth metals to a healthcare professional who's been in this for a long time, like a physician or a pharmacist, somebody who's really studied this deeply, right? Pharmacology deeply. When you say alkali metals, you're like, there's a certain charge on all those atoms, and we'll get to that later. But these names are actually pertinent for people in healthcare, which is why we're telling you these. Noble gas. If you say noble gas, immediately, a pharmacist is probably thinking, an inert gas, a non-reactive gas. So, and if you say halogen, they're thinking, very reactive gas, or they're thinking anion. So these names actually have meaning to you as a healthcare professional. So I said that you can't change the number of protons and have the same atom, but you can change the number of electrons and you can change the number of neutrons. So when elements have a different number of electrons than the number of protons, we have something called an ion. So if you have 5 protons but 4 electrons, you have an ion because you have a charge, right? +5 minus 4 equals +1. You have a +1 charge. It's what we call a cation. So when the electrons and the protons are not equal, you have an ion. When the electrons and the protons are equal, you have what we call a stable element. There's no charge, overall charge, because the charge and the electrons and the protons cancel each other out. You can also change the number of neutrons. Elements that have different numbers of neutrons are known as isotopes. So if you have helium with 2 neutrons, that's one isotope of helium. If you have helium with 3 neutrons, that's another isotope of helium. It's still helium, which is a different number of neutrons. So let's go over ions first. So ions lose and gain electrons through a process called ionization. That's just when they lose or gain electrons, right? Positive ions are called cations, negative ions are called anions, and the charge is always written in the upper right-hand corner of the atom. So here, calcium 2+ means that this guy has lost 2 electrons, right? Because you have 2 negative charges that are gone, so there's an extra 2 positive charge. So this calcium atom right here has 2 extra protons, or I guess 2 less electrons, if you think about it that way. Probably a better way to think about it. You can calculate ionic charge by just taking the number of protons and subtracting the number of electrons. Works every time. Just make sure that if you're subtracting a negative, you're adding, right? So here, lithium, if you have lithium plus, right? Lithium, if you look it up on the periodic table, has 3 protons. So you would take 3 minus, here you've lost an electron, -2, and you would get a +1 charge. Same thing if you're looking at an anion. So let's say fluorine has an extra electron. You have a stable fluorine, right? But you're adding an electron to it, it'll have a -1 charge because fluorine has 9 protons. So if you're subtracting 10 electrons, then you'd have a -1 charge. And you can kind of predict these things by looking at the periodic table. All the alkali earth metals want to have a +1 charge. All the alkaline metals want to have a +1 charge. All the alkaline earth metals want to have a +2 charge. Most things in 3A tend to have a +3 charge. Group 4, 4A, they can be plus or minus 4. 5A tends to be -3, 6A tends to be -2, 7A tends to be -1, and 8A doesn't want to be charged at all. So pretty much if you see something in the 7A column, you know it probably has a -1 charge. If you see something in the 2A column, you know it probably has a +2 charge. You just have to kind of memorize that. This is a good table right here that helps you understand that. Notice that boron's not in there, right? It's kind of a tricky one. Carbon's not in there. It's kind of a tricky one. But the ones that are filled out are pretty stable. Like pretty much everything under 7A, 6A, 1A, and 2A are going to follow this pattern. And that gets really helpful later when trying to figure out what a charge is going to be on an atom. Now let's also talk about isotopes. So all atoms have naturally occurring differing kinds of isotopes, right? So if you take like a neon sign and you take some neon out of it and you sample it and you start looking at all of the neon in it, you're going to find out that some neon has 10 neutrons, some of the neon has 11 neutrons, and some of the neon has 12 neutrons. And that just kind of comes from the beginning of the universe when everything was cooling down and all the elements were being irradiated with all of the radiation that was coming from our sun, and et cetera, and et cetera, et cetera. We just ended up with some neon that has 10 neutrons, some that has 11, and some that has 12. So all the atoms have isotopes, right? And there's a certain natural abundance of all of those. If you look at a sample of neon, right? Let's say you pull neon out of the air, because there's tiny little bits in the air, right? You're going to find that about 90% of the neon has 20 things in its nucleus, so it has 10 neutrons, and you're going to find about 10% has 12 neutrons, and you're going to find a tiny little fraction that has 11. And these percentages that you see here are they're just a fact of nature. Like nature created neon with these many, with these types of neutron isotopes, with these number of neutrons in this kind of, I guess, just mix, you know? And there's a lot of reasons for how this happened on a very like deep radiochemistry, quantum physics, quantum chromodynamics level. But in this class, you just kind of have to press the I believe button and accept the fact that these ratios just kind of exist as they are. So when we talk about isotopes, we want to be able to denote them with symbols, right? Because we usually denote elements as symbols. And the way that you do this, putting the mass number on the top left of it and the atomic number on the bottom left. So remember when I said atomic number, that's number of protons, Z. We're writing the atomic number on the bottom. We write the mass number, which is the number of everything in the nucleus, to the top left. And then you write the chemical symbol. So for example, neon has 3 different isotopes, has 10 protons. You can get that by looking at the periodic table, right? Look up neon, it's atomic number 10. And then you can say, okay, well, if it has 10 neutrons, 10 plus 10 is 20. So neon 20 has 20, 10, and then Ne for its symbol. And if it has 11 neutrons, it would be 21, 10. And if it had 12, it would be 22, 10. You can also just kind of write it like this with the chemical name dash the mass number. So to put the number of protons, just put the number of things in the nucleus. So what do I talk about like when I say mass number and atomic mass? Those are totally different things, actually. So atomic mass is how much an atom weighs. So think about this. This might blow your mind. If you have neon 20, neon 21, and neon 22, they all have different numbers of neutrons, right? So what's the mass of neon? Well, all of the isotopes have different masses, right? So we have to kind of average all those masses together when we talk about the mass of neon. Otherwise, you'd have to say, well, I have some neon. 90% of it is neon 20, and that has a mass of this. And then, you know, we want to just be able to talk about neon by itself, not the isotopes, to average all that stuff together, right? And so when we talk about mass, we use something called the atomic mass unit, and we'll discuss how we come up with that later. But the fact is we have to kind of average all of these things together based on their abundances. So if neon is kind of in this, you know, distribution where 90% of it is one isotope and 10% is another, and this tiny little fraction is another, you know, but the periodic table says the weight is 20.18 AMUs. How did they come up with that? Well, they took an average of all of these masses. They basically said the fraction of isotope 1 times the mass of isotope 1 plus the fraction of isotope 2 times the mass of isotope 2 plus the fraction of isotope 3 times the mass of isotope 3 equals the overall weight of that. And so what does that look like if we were to do that by ourselves? Well, let's say that we have we're looking at chlorine, right? And let's say that we look up in a textbook, and the textbook tells us 75.77% of all chlorine is chlorine 35, all of it. And then 24.23% of chlorine 30, of all chlorine is chlorine 37, right? And we get these masses. If you wanted to translate these percent abundances and atomic mass units into the periodic table value, what you would see on the periodic table, you basically just have to multiply each abundance by the weight and add it, and add them all up. So you just follow this formula right here: fraction of isotope times mass of isotope plus fraction of the other isotope times mass of the other isotope to get a total. It's just an average of all of those. So like this is totally on the quiz, right? Like it's going to ask you to do these calculations. So make sure that you kind of go through this, step through the math and like figure out, okay, how does this work? If you do, you're going to be able to answer the questions on the quiz just fine. And I just want to give you an aside really quick. Isotopes are important to you as medical professionals too, because we use them in medicine. Like F18 is an unstable isotope of fluorine that's used in like cancer diagnosis, right? Iodine 131, we use it to kill thyroid cells to help in the treatment of hyperthyroidism. And technetium 99 is actually a metastable isotope of technetium that we get from molybdenum that's used in medical imaging. So this stuff is real. Like you might come across this on the job. So let's just do some sample quiz questions. Start out simple, okay? An element has 4 neutrons, 4 electrons, and 3 protons. Which element does this describe? Is it a neutral atom, isotope, or an ion? What is the mass number? What is the net charge? Literally a quiz question. Like it couldn't get more quizzy than this, right? So if you can answer this, you're going to do really well. So where do you even start thinking about this? Well, the number of protons tells us it's lithium, right? Since the atomic number is 4. If you go to the periodic table and you say, okay, oh shoot, the atomic number, I messed this up. The atomic number is 3. This is a typo, my bad. I'm on a new computer and my fingers got 3. So it's number 3. Hopefully you're watching and not just scanning through this, or it's going to really confuse you. But so the number of protons is 3. Atomic number is 3. Okay. So looking at the atomic mass, we see it's about 7, right? That's the number you get for the atomic mass. So you think like, okay, 3 plus 4 is about 7. So it's not an isotope, right? It's what you would expect. That question, is it an isotope? I'll say this, the quiz asks some really poorly worded questions about like, is this an isotope? If you get those wrong and everybody gets them wrong, I typically like throw those questions out, so don't worry too much about them. But this one's important, right? So looking at the number of protons, we have 3, right? But we have 2 electrons. So what would the charge be? Well, remember, positive 3 plus 2 negatives, so minus 2, leaves us with a positive 1. So this is a cation with a positive 1 charge, right? So you have lithium plus, that's the identity of this atom. So be able to kind of think about how this works right here. If you had the number of protons, go to the periodic table, look it up, right? That tells you the element. And then start thinking about, okay, like what's the number of protons plus the number of neutrons, looking at the mass, okay, is it an isotope? How many electrons are there in relation to the number of protons? Will it have a charge? It's kind of how you do that. So let's move on to the math portion of module 2 now. Avogadro's number, I brought it up earlier, and it's just kind of something that you have to learn, but it's really great to learn because if you go into nursing, pharmacy, medicine, whatever, you're gonna have to do unit conversions, right? Module 1, we had plenty of unit conversions, and Avogadro's number is just another unit conversion. It's just another way to convert numbers. So when I say Avogadro's number, what do I mean? Well, some numbers have words associated with them. If I say a dozen, you intuitively know that means 12, right? If I say a week, you intuitively know that's like 7. If I say a fortnight, you might know, if you speak really good English, that it's 14. Words pretty deprecated now, but you understand, like if I say a gross, that's 144, right? Avogadro's number is the same thing. Avogadro's number represents what we call a mole of anything. Okay, so Avogadro's number is 6.02 times 10 to the 23. It's just a number. But that 6.02 times 10 to the 23 is the same thing as saying a dozen. Like 1 mole of anything is 6.02 times 10 to the 23 of that thing, just like 1 mole of a thing is 12 of that thing. So it's just a much larger version of a dozen. Hopefully that makes sense. Hopefully the 10 to the 23 doesn't freak you out or anything. You know, it's a really, 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 really big number. But we represent it as just one of something because it's easy to work with, right? And the reason we use 6.02 times 10 to the 23, we'll get to later, but just understand 1 mole of anything is 6.02 times 10 to the 23 of that thing. So 1 mole of dollar bills would be equal to 6.02 times 10 to the 23 dollars. Just like a dozen eggs is 12 eggs, a mole of eggs would be 6.02 times 10 to the 23 eggs. So a mole is just another word like a dozen. Don't let it freak you out. Why is it such a large number? Yeah. I mean, really, the reason is because we have to have a lot of molecules to make up something physical that we can see and touch, right? For example, 22 real copper pennies contains about 1 mole of copper, okay? So 22 pennies, there's about a mole of copper in there. If you have 2 large helium balloons, they contain approximately 1 mole of helium. So 2 large helium balloons contains approximately 6.02 times 10 to the 23 molecules of helium, right? So yeah, where does it come from? Okay, the numerical value is equal to the number of atoms in 12 grams of pure carbon-12. Why pure carbon-12? Because it was something easy to measure back in the day when we were establishing all this stuff. So it establishes a relationship between the mass of something, grams, and the number of atoms of that thing, the mole. That's incredibly important. And hopefully through this course, you start to understand why. I can weigh something like carbon, but I can't take really tiny tweezers and count individual atoms of carbon, right? I can't do that. I don't have the technology really to be able to do that. We might. There's some really cool stuff being done with lasers, but the point is, like, with Avogadro's number, I can start to use a relationship between the mass of something and the number of things that relate to that mass. So that's cool. It's cool because all of a sudden, let's say that I need a certain number of atoms or molecules of something, I can convert that into the weight of that thing. And the weight of that thing is something I can measure. So let's do some examples. So 3.5 moles of helium. How many moles of helium is that? Well, 1 mole equals 6.02 times 10 to the 23 helium atoms. 6.022 is also right. Sometimes I'll go back and forth, sorry. But really what you need to do is just set up a conversion factor, just like we did in Module 1. You know, you can 6.022 times 10 to the 23 helium atoms on top over 1 mole. You can flip it to whatever you want to do, but it's nice to have it on top because if you do this 3.5 moles of helium times your conversion factor, you get moles on top and moles on bottom. They cancel out, you get 2.1 times 10 to the 24 helium atoms. So very easy, simple way to do this. Same way if you're going kind of the other way, if you want to go to atoms to moles, then just flip your conversion factor and put Avogadro's number on the bottom. That way Avogadro's number cancels. You know, the units cancel, you know, silver atoms on top, silver atoms on bottom, and you're left with moles, which is what you want. So very, very kind of easy concept to work with, just a big number that kind of confuses people. So you can convert moles to number of atoms and atoms to number of moles, but what if you want to convert mass to number of atoms? I said that was really important, right? Because we want to be able to like figure out like number of things related to its mass. It's very powerful. So we use the molar mass to do this. What is it? Well, I said that atomic mass and Avogadro's number all kind of have some relationship to one another, and that relationship is through carbon-12 because Avogadro's number is based on carbon-12, right? It's a number of carbon-12 atoms in 1 mole of carbon-12. All of a sudden we can start to relate the mass of carbon-12, and because everything is aligned around this one isotope of carbon, it sets up kind of a ruler from which we can start to measure everything else. Basically because of this, the atomic mass of carbon-12 is 12 atomic mass units. Because we have this relationship between through this one atom, we're able to basically state that 1 mole of atoms of any element is equal to its atomic mass. So basically, if you want the atomic mass of something, you just go to the periodic table and you look up its atomic mass, and that will give you the molar mass. So if I want to know the molar mass, if I want to know how many grams of copper are in 1 mole of copper, I can go to the periodic table and look at the atomic mass, and that will tell me what this 63.55 under copper means. The real true significance of that you care about is that if you have 1 mole of copper, it's going to equal 63.55 grams. It's literally what that means. So what's cool is you can convert between grams and number of atoms. Very cool, because all of a sudden I can weigh something, right, get its mass, and then figure out how many atoms of that thing there are. The first thing you have to do is go through the mole to do that, right? So let's do that as an example. Let's calculate the number of moles of carbon in a 0.58 gram diamond. Okay, diamond is just straight up carbon, right? So basically you want to set up your conversion factor. 12.01 grams of carbon is equal to 1 mole. You get that from the periodic table, right? So you set up your conversion factor. There's 12.01 grams in 1 mole of carbon, or you can say there's 1 mole of carbon in 12.01 grams of carbon, right? You can flip this up or down, right? If you leave moles on the top, then grams of carbon cancel. You can just cross multiply, and you come up with 4.8 times 10 to the minus 2 moles of carbon in 12.01 grams, or in 0.58 grams. But now what if you want to go all the way to like the number of atoms of carbon, right? Then all of a sudden you have to throw in another conversion factor. This is really important too for the quiz. This is like super, super important. If you're going between mass and the number of atoms or something, you got to go through the moles. It's a 2-step process, okay? So that's what we're going to show you here. So we can go from grams to moles using the conversion factor that we get from the periodic table, but then you got to go 1 step further and use the conversion factor with Avogadro's number to get to the number of carbon atoms. So let's just forget about that example and we'll go to a different one and start over new, okay? So how many aluminum atoms are in an aluminum can with a mass of 16.2 grams? This should tip you off. How many atoms are in a can with a mass of 16.2 grams? You're going to go from grams to number of atoms, or from number of atoms to grams. You're not going to the mole, but the mole still is the connection between these two things, right? So if you look at the periodic table, you see there's 26.98 grams of aluminum in 1 mole of aluminum. Again, you just look at the periodic table for aluminum, see that the atomic weight is 26.98 AMUs, and that tells you it's 26.98 grams of aluminum in 1 mole. And then you know that 6.02 times 10 to the 23 atoms of anything is equal to 1 mole of anything. So you have your 2 conversion factors right there, and you can set them up. And again, you can flip these either way. You can have 26.98 on the top or on the bottom, whatever. You just want to make sure it makes sense that when you cross multiply and divide and et cetera, that everything cancels out nicely, right? Which is why we have moles of aluminum on top here, and we have number of aluminum atoms on top here, because grams of aluminum cancels in this calculation, and then moles cancels in the second. And you get 3.62 times 10 to the 23 aluminum atoms. So again, 2-part problem. Don't forget to go through the moles here. You have to. It's the link between mass and the number of atoms or molecules. Yeah, let's say, what about molecules? So 1 mole of atoms equals 6.02 times 10 to the 23 atoms. Cool. 1 mole of molecules equals 6.02 times 10 to the 23 molecules too. So notice the difference here. Like, molecules are comprised of atoms, so 1 mole of molecules has more than 6.02 times 10 to the 23 atoms, right? If you have a molecule with 2 atoms and you have a mole of that molecule, you have twice as many atoms. So how do you convert grams and moles and et cetera for molecules? How's it different? Well, let's look at water. That's an easy one, right? H2O. So calculate the mass in grams of 1.75 moles of water. Well, the molar mass of hydrogen from the periodic table is 1.01 grams per mole. The molar mass of oxygen is 16.00 grams per mole. So basically you want to add all that up to get the total molar mass of water. So say 2 times 1.01 for hydrogen, plus, because there's 2 hydrogens, plus 1 times 16, because there's only 1 oxygen. The total overall molar mass for water is 18.02 grams per mole. So just going to have to add everything up, all the elements. Now I have a molecular molar mass, right, that I can then use with this new conversion factor to get 31.5 grams of water. Let's do it for nitrogen dioxide as well. Same principle. So we get the molar masses from the periodic table. all we have to do is then multiply each of those by the number of them there are. So there's one nitrogen, so we're going to say, okay, the molar mass of nitrogen is 14.01, and then we're going to add that to 2 times 16, which again is the molar mass of oxygen, and we get 46.01 grams per mole. So 46.01, that's our conversion factor, right? We want to have, we want to go from number of molecules through the mole. So we want to have number of molecules on top and bottom so they cancel. And then we want to use our grams per mole conversion to get to 365 grams of nitrogen dioxide. Now, I flew through all of that, right? Because it's 36 minutes into the lecture. I'm supposed to keep it at 60 minutes so that I'm not like overwhelming you. But go through and watch that again. Like pause it, look at the math, look at how it's being conducted. The more you do these conversions, the more it's going to make sense. So, and you'll do similar conversions on the job in the healthcare setting, I promise you. Let's put the math aside and go to a more conceptual portion of this lecture, which is the intro to quantum mechanics and electron configuration. So why are we even talking about all of this? Well, electrons, are probably the most important part of an atom. And the reason for that is because electrons are what are responsible for bonding. They're responsible for reactivity. Electrons interact with light, and light is something we can control to study atoms and molecules. In fact, it's the interaction of light with electrons that has helped us understand like what the atom, like basically what the properties of the periodic table are on a very fundamental level. So I guess we should talk about like light first before we really get to talking about the electron, because light is what we use to study the electron. So light, you might have heard, is just a form of electromagnetic radiation, right? Electromagnetic radiation is light. Light is electromagnetic radiation. Whatever, it travels really fast through space. You don't have to know that number, it's just really, really fast. Light has properties of both waves and particles. The important thing, though, is it can stimulate electrons. It can excite them and interact with them. Light has what we call symmetric overlap at certain energies with electrons of certain energies, and those electrons can interact with light. That's really cool, right? I don't have tiny tweezers where I can move an electron around, right? But I can shine light at a certain energy at an atom and make an electron do what I want. That's very powerful. So yeah, let's just talk about light really quick because it's this powerful tool, right? We talk about things like wavelength and frequency. The quiz is going to have a question about the interrelation between these two things. Wavelength is basically the distance between the crests or the troughs of a light wave, right? And the frequency is basically how fast those troughs or crests pass through a certain point. And I guess the important thing to really understand here is that there's this relationship between frequency, wavelength, and energy. And the big takeaway is this kind of last bullet here. This is on the quiz. It's in the test bank on the quiz, so focus on it in case it comes up on your quiz. Light waves carry more energy if their crests are closer together, shorter wavelength, higher frequency, right? So if their wavelengths are shorter, they have a higher frequency because those crests are moving through the same period at the same rate, or at a faster rate. And that all means higher energy. So higher frequency, shorter wavelength, higher energy. Lower frequency, longer wavelength, lower energy. Just remember that for the quiz, important. So something that I just want to dispel really quick. White light is a range of many different wavelengths. So the white light that you see ambiently coming from the sun or from full spectrum light bulbs or whatever is actually made up of many, many, many different wavelengths of light. If you pass light through a prism, you can break it out into red, to all the colors of the rainbow, which is actually how rainbows work, right? It's diffracting light into its components. But light is more than just color, right? Light's like this tiny little sliver of the electromagnetic spectrum. Light is actually radio waves. Light is microwaves. Light is infrared radiation, ultraviolet radiation, X-rays, and gamma rays. All of this is light, electromagnetic radiation, right? We just see visible light in this tiny little sliver because it's what our eyes have evolved to see. You know, like certain insects can see ultraviolet radiation, for example, right? I think certain animals can see a little bit of infrared radiation. The James Webb Telescope only looks pretty much in the infrared radiation spectrum, maybe like the near IR, like red portion of the visible spectrum, right? So all of it's the same stuff. It's all photons. It's all light. It's just different energies. So this arrangement of energies is actually another quiz question on the on the quiz in the test bank. Just understand, like, radio waves are very long, huge, you know, on the order of meters, and they have very low energies. And then you go all the way up to gamma rays, and these have very, very, very short wavelengths, but they have very high energy. And, like, you know, it's just an aside for you guys too, like, light is important to medical professionals because it's used as treatment. Like, we use X-rays and gamma ray beams to kill cancerous tumors, and we use ionizing radiation to stop, like, to you know, create errors in cancer's DNA so that they can't continue to grow, right? So light is actually used therapeutically in medicine. So we have light. You know, it's important for you to understand this electromagnetic radiation. Electromagnetic radiation, you know, has the spectrum under everything. And there's high energies and low energies. But again, light's important because it allows us to study the electron. And the electron is important because it allows us to study reactivity. And that tells us kind of like what compounds we can form, what bonds we can make, you know, it just, electrons are what chemists really want to focus on because they're what tells us what we can build. So studying how light interacts with electrons gave rise to kind of two different theories of the electron and how it interacts with the atom. One is called the Bohr model, and the other one is called the quantum mechanical model. And the Bohr model is kind of the first one, right? It's not super perfect, but it has a pretty decent description of what's going on. It treats electrons as particles, and it basically says, okay, these particles are kind of orbiting a nucleus on very specific orbits. And these orbits are called the principal quantum number n. Okay, so there's all these different orbits. These orbits can, you know, correspond to different energy levels. So the orbit closest to the nucleus is the lowest energy level, and every orbit higher than that is a higher energy level. So keep increasing energy levels as n increases, right? So n1 is that first orbit, much lower in energy than n4, which is 4 orbits higher, right? So it's the Bohr model of the atom. But the thing is, like, the Bohr model didn't really understand it. It fell apart after hydrogen, basically. It wasn't able to really capture exactly why electrons were doing what they were doing. It wasn't able to predict the energies that electrons would have. So a few other physicists came up with the idea of the quantum mechanical model, right? Basically, what the quantum mechanical model states is that instead of these like specific orbits, you now have these kind of probabilities of where an electron could be at a certain energy. So instead of like a fixed orbit, you've got kind of a probability space, like, the electron might be there. That's the big difference. So instead of those orbits, you now have these kind of clouds, right? And this cloud is basically saying the electron's kind of, its existence is kind of smeared all over this whole area. So an electron can be in this area. So in this, you know, in this model, basically, there's these different kinds of orbitals, not orbits, but now orbitals, and they have different shapes. These orbitals are called, or I guess abbreviated SPD and F. Okay, and each one of these orbitals, or we also called subshells, right? Has its own shape, as I mentioned. So, like, if you look at the s orbital, for example, it's just a sphere. So it basically means there's 2 electrons possibly in this area, in this orbital. So each of these s, p, d, and f like orbitals also exists in like a bigger what you would have thought of as the parent orbit, like the principal quantum number n. So n still exists, you know, but these are kind of like tucked within that, and it's something that your brain can't really wrap its mind around because things just get a little bit goofy way down at the atomic level. So think about this left-hand column, the shell, as the orbit in the Bohr model, right? The big orbit. And think about these subshells or orbitals as like kind of sub-energies within those big groupings, right? This is important right here, this graph. Basically, what you need to take away from this is that the n equals 1 principal quantum number, right? That first orbit, that lowest energy orbit, only has one orbital, only has one subshell. That's the s. The n equals 2 principal quantum number has two subshells, two orbitals, s and p. The third principal quantum number has three subshells, s, p, and d. And the fourth principal quantum number has s, p, d, and f. Okay, so you kind of notice a little bit of a pattern here. And I guess I'll ask the live session question now. Even though I think I ask another one later, but this is a good one. So if you answer this one, you're fine. Does the d orbital exist within the n equals 2 shell? Okay, just to start thinking about that, right? So there's your question for that. So let's go into each of these subshells. So I said the s orbital looks kind of like a sphere, right? What it means is that there could be an electron anywhere in that blue blob. Actually, there could be two. There can always be two electrons in an s orbital. The p orbital looks like this. It looks like some kind of dumbbell thing. Basically, what this means is that in the p orbital, there's three different orientations. There's one that aligns itself in the x, the y, and the z, and each one of these can hold two electrons. So you can put two in here in the x, two in the y, and two in the z orientation. So that means the p orbitals can hold 6 total electrons, right? You get the d orbitals, they're crazy looking. I mean, like, you have these 4 lobes and they kind of align themselves in different planes. You have the y, z, x, y, x, z, you have the x squared minus x, y. And then you have this really strange shape, which, I mean, really think about this. In the donut between the dumbbells and that white space, it means that there's no probability, it's impossible for an electron to exist in that area. I guess not impossible, but it's highly unlikely there will be an electron in there. But there's probably an electron either in the ring or in one of those lobes. Actually, there's 2. So again, you can fit 2 electrons in each of these, so the d orbitals can hold 10 total electrons. So this is like totally on the quiz. The quiz, like in the test bank, there's a question that asks you, like, what's the shape of the orbitals and how many electrons can they hold? And again, like, what do they exist within? Note that the f orbital only exists in the 4th principal quantum number, the d only in the 3rd and the 4th. So this table is kind of important on the quiz, you know. Remember this terminology here: sphere, dumbbell, clover, flower, 2 clovers, if you get it on the quiz. So I guess I just want to drive the point home that, again, the principal quantum numbers corresponds to increasing energies, but so do the orbitals. Notice that if I have the 1s orbital, there's no other suborbitals besides s. But as soon as I get to the 2, the principal quantum number, right, there's an s and a p orbital, right? There's an s, and then there's those 3 configurations of p. P orbitals are at slightly higher energy than s orbitals, okay? So electrons that are in the 2s orbital are going to be lower in energy than electrons that are in the 2p orbital. And the same kind of pattern repeats for the 3p, 3s, 3d, and then the 4th principal quantum are kind of the same thing. And note here, it's kind of strange, the 3d orbitals are a little bit higher in energy than the 4s. So they can actually, the suborbitals can actually be bumped a little bit higher than the principal quantum number. So just understand that the suborbitals, you know, the subshells, the orbitals, whatever you want to call them, also have kind of a hierarchy of energy. And that's definitely on the quiz as well. The p orbitals lie higher in energy than the s orbitals. The d orbitals lie higher in energy than the p orbitals, but only within their principal quantum number. Sometimes, you know, that might not be true if their principal quantum number is different. So when we talk about an atom and we want to talk about the energies of its electrons, the best way to do so is using something called an electron configuration. An electron configuration basically just says, what orbitals are populated with electrons. And the simplest would be for hydrogen. Hydrogen, if you go to the periodic table, it's element 1, has 1 proton. So for a stable hydrogen element, you'd have to have 1 electron, right? So that 1 electron has to exist somewhere. And in the ground state, in its lowest energy state, it's going to be in the lowest principal quantum number with the lowest shell, right? Lowest subshell. So it's going to exist within the 1s orbital because that's the lowest in energy, right? It's the lowest energy orbital. You can see it right there, right? So we denote that by just writing the orbital 1s, and then by putting a superscript to the right. This is how many electrons there are in that orbital, 1. So the ground state of hydrogen, the lowest energy state, has a 1s1 electron configuration. That's what stable hydrogen looks like when its electron is in its most stable form. So, the idea here is that you can do this for really any atom as long as you follow a couple of rules. Anytime you want to know the electron configuration of an atom, you want to always start filling electrons in the lower energy orbitals going higher. So start in that 1s and then go to 2s, 2p, 3s, 3p, 3d. Just keep going up. You have to understand that orbitals can hold no more than 2 electrons each. So the s orbital can only hold 2 electrons. The p orbitals, there's x, y, and z, can each hold 2. So p can hold a total of 6. The d, 10, and so on. And then when orbitals of identical energy are available, all of these are first occupied singly by electrons and then in pairs. Electrons don't like to be paired up. They like to be single. We don't have to worry so much about that rule in this course, but the second one is very important. So let's just look at a couple of these examples. Let's look at nitrogen. If I look at nitrogen on the periodic table, I see that it has an atomic number of 7. That means it has 7 protons. So to be stable, it has to have 7 electrons, right? Because if it had a different number of electrons, it'd be an ion. It means it's charged, it's not stable. So nitrogen in its stable form has 7 electrons. I know that from the periodic table. Basically, what I'm going to do is just start looking at this, graph right here and just start putting 2 electrons in each of these. We do that by drawing little arrows, right? So I kind of reformed that here. I drew the 1s orbital. I put 2 arrows in there, put 1, 2, okay? And then I drew the 2s orbital, put my 1, 2. And then I have my 2p orbital, and I put single electrons in each of those, and then that equals 7. 2 plus 2 plus 3 is 7, right? So this is kind of what the electron configuration looks like if you draw it out. But then you just start kind of writing what you have. You have a 1s orbital with 2 electrons, right? This is a superscript. You have the 2s orbital with 2 inside of it. And you have the 2p orbital with 3 inside of it. So the electron configuration of nitrogen in its ground state, its most stable form, is 1s2, 2s2, 2p3. Oxygen shouldn't be surprising. If you look at it on the periodic table, it's right next to nitrogen, so it has 1 additional proton, which means it has 1 additional electron. And there you would say, okay, well, I'm just going to draw another arrow. Okay, I'm going to write 1s, count the number of electrons, 2, 1s2, fill up my 2s orbital, okay, 2s2, and then 2p. When I fill up, I start matching, up here and get 2p4. Fluorine is 1s2, 2s2, 2p5. Neon is 1s2, 2s2, 2p6. So it's kind of, it looks confusing, but really it follows this pattern that becomes really simple the more you kind of look at it. What's neat too is that when you're writing electron configurations for elements beyond neon or beyond any noble gas, you can use the what we call the noble gas configuration. Basically, if you look at sodium, for example, it's element number 11 on the periodic table, and it comes right after neon. If you don't want to deal with 1s2, 2s2, 2p6, that's neon, right? You can just take all of that and bracket it and say neon basically symbolizes 1s2, 2s2, 2p6, and then just write 3s1. What's also neat about this is that if you look at where sodium is in the periodic table, what row is it in? It's in the 3rd row, right? So you can kind of start saying, okay, well, neon was in the 2nd row. I'm going to write neon in brackets, and then I'm just going to start with the 3rd principal quantum number because I'm in the 3rd row, and then just start from there. 3s1, 3s2, 3s2, 3p1, 3s2, 3p2, and so on and so forth. So what about ions? What if you have sodium plus, right? So we said sodium had this neon 3s1 electron configuration, right? But if you have sodium plus, it means you have one less electron, right? Because plus means that there's one more proton than there are electrons. So you have, one electron must have gone away. So what would that look like? This is 100% a quiz question, like 100%. Please don't miss this on the quiz. And it won't be for sodium, it'll be for something else. But just understand it's going to have the electron configuration of whatever is behind it in the periodic table, right? You're going to lose that 3s1 electron, so it just looks like neon, right? So what if you're given a configuration, you're trying to figure out what the element is? How do you do that? We'll just go to the periodic table. Start with row 3. You're at 3p2, you know, and you're going to do 3s2, 3p2. You know, don't worry about the 1 and the 2. You know you've already gotten through the 2 rows of the periodic table, and just go over 4 elements because you have 2 electrons in the third principal quantum number, right? Or you could just count all the electrons. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 2 is 14. You can go to the 14th number in the periodic table, 14th element, and you get silicon. So either one of those methods is fine, but that's really all you have to do. Either count the number of electrons or just go to the row based on the highest principal quantum number and just go that number of electrons over. Seriously, quiz question. Like this will definitely be on there. Like I think no matter what test bank you get, some kind of question like this will come up too. So let's make sure that we really ask this last session question again. Like, does the 2d orbital exist? I asked it earlier, right? So think about it. Like, does it exist? And don't look at that graph, that table. Now think about it in your mind. Like, would it exist? Does the d orbital exist in the second principal quantum number? Is this an actual orbital? Is the 2d orbital real? Let's just talk a little bit about core versus valence electrons really quick. I said electrons are really important because they do things like participate in bonding and they're reactive, right? And they elucidate properties of atoms, right? The valence electrons are the electrons that are kind of on the outside of the atom, and they're the ones that kind of like do all this reactive bonding stuff, right? So valence electrons are really, really important. Electrons that are not on the outside, right? They're not in the outermost principal quantum number or principal shell. They're not the farthest highest energy ones, right? The ones that aren't these really outer electrons are called core electrons, right? So you can kind of look and note which ones are core and which ones are valence because all of your core electrons are going to have the lower principal quantum numbers. In silicon, it's the ones that are in the first and second principal quantum number. And your valence electrons are the ones in your higher principal quantum number, the ones that are associated with the third principal quantum number because it's the highest, right? So don't get confused if you see something like selenium, for example. 3d electrons in selenium are actually higher in energy than the 4s2 electrons, right? They just are. It's a weird quirk of the d orbitals when you start getting up in energy. Doesn't matter. The valence electrons are still the ones that are in the fourth principal quantum number. It's the most important one when determining whether something is a valence electron or a core electron. So selenium has 6 valence electrons, right? It doesn't have like 16 or whatever you might think here, or 12 or whatever. And this is just a little table to kind of help you figure out like the number of valence electrons. Like, you know, look at boron, for example. It's 2s2, 2p1 valence electrons, right? That's what the electrons are. So there's 3 valence electrons. You can also kind of count the main group atoms. Their number of valence electrons is going to be their group number. So, you know, for example, fluorine has 7 valence electrons because it's in group 7a. So I kept it to an hour exactly. I'm very proud of myself because usually I drone on and this ends up being an hour and a half. But in review, we covered a lot of stuff. So basic atomic theory, what is an atom, neutrons, protons, electrons, the way that the periodic table is periodic and the way that it's laid out, right? Repeating patterns and names and metals and metalloids and nonmetals and transition elements, etc. Isotopes and ions, the number of protons tells you what the atom is. The number of neutrons and the number of electrons can change. They tell you whether it's an isotope or an ion. Avogadro's number of molar mass, it's just another conversion factor. It's just module 1 over again, but this time answering a different question. You're just making a conversion factor with the molar mass from the periodic table or with Avogadro's number and its relationship to the mole. Remember, 6.02 times 10 to the 23 equals 1 mole. And then doing some math with that. It's exactly like the same. It's the exact same math from Unit 1, just with a different number. Then we went over the Bohr model and the quantum mechanical model. Bohr model, really the takeaway from that is a simple kind of model with like these orbitals, or sorry, with these orbits, and each one has a principal quantum number, but it didn't exactly describe what was going on with electrons. So we came up with the quantum mechanical model, which is much better, which gave rise to electron configurations, which is a shorthand way for us to talk about the energies of electrons in an atom. So I know it was a lot. Make sure that there's some peer tutoring that you can get at the Learning Center if you need that. If you need some kind of outside materials to help you study, or some, I always suggest Khan Academy because it's brilliant, but the library is a really great resource for pointing you in the right direction if you need help with something. And you can always reach out to me or consult your textbook, because it's got a lot of questions in it, like sample questions that also kind of show you what might be on the quiz too. But in the end, I think studying what I tell you in the lecture is going to be on the quiz is probably your best bet for preparing for it, because I really try to give you the best heads up I can. And with that, I'm going to end the recording and I'll stick around to see if there are any questions. Just give me 1 second to figure out how to stop this.